Recording. Hi everyone, welcome back. This is part 2B of homework 2. Now in the last part we explained and coded the secant Newton methods, and we're going to expand on this Newton method a little bit for part B, which is going to be explain and implement Newton's method for finding the root of a vector function or n-dimensional function. So over here I have pulled up here basically a system of equations where we have k variables and k functions. Now, what we coded before was for a one-dimensional function, Newton's method for a one-dimensional function. But how would we do this for basically a system of equations with many variables and many functions? And actually, it just tells us right here how we would do this, where we take our initial guess minus the Jacobian of our initial guess, the inverse of that Jacobian, multiplied by the actual function value of our initial guess, which is what this big F is. And so this is matrix multiplication between these two. And that's going to go ahead and give us our new x value, and we will basically iterate this until we find the root of our system of equations. And just reading this, one may also use Newton's method to solve a system of k equations, which amounts to finding the simultaneous zeros of k continuously differentiable functions. So this should give us, we should find the zeros of our k functions using this method. So we're going to need the Jacobian, and I actually talked a bit about the Jacobian in homework 1, so I'm not going to speak too much about it here, only that it is basically an array of the Jacobian matrix. It's a matrix of basically derivatives of our different functions with respect to each variable. So it'll look like a square. The Jacobian matrix will be a square, and it says that right here. It's k by k Jacobian matrix, since we have k functions, and each function will be with the derivative with respect to each variable. So just to start coding this out, we'll define a new function. We'll call it capital Newton's method, capital Newton's method. And it's going to need a function, big F. It's going to need an initial guess, one initial guess. So this is just like before. This is just like up here. We'll have our max iterations, 50, and our tolerance equals 1 times 10 to the negative 10. Now, we're going to need to have the Jacobian of our function. So we will need to specify a function, and we'll do that after we write this. After we write this function here, we will specify our function f. So we'll have f Jacobian of f, and that's going to equal the Jacobian of f. And actually, Jack's, just like we used Jack's dot gradient before, or Jack's dot grad, we can use Jack's dot Jacobian of f, of our function f. And we'll have f1 equals our function f at the point x0, so our initial guess, at the point of our initial guess. And that should be everything we need. We need the inverse of the Jacobian multiplied matrix multiplication by the function. So if I were to code that in, we're going to have basically x1 equals our initial guess minus our inverse of our Jacobian at our x0. So we have our Jacobian here, but we need the inverse of that. So we can use this function called jnp dot, I believe it's linear algebra dot, I believe it's this one, inverse of f jack at the point x0. Is that right? Yes, xn will be x0 for us. So that'll give us the inverse of that Jacobian matrix. And then we'll use the at sign to specify matrix multiplication with f0. And actually, I believe I wrote this incorrectly. This should be f0 equals f at x0. Let me just check over this real quick. x0 minus the Jacobian, the inverse of the Jacobian at x0, multiplied matrix multiplication by f0. Okay, so that should give us our new x value. And then we'll have f1 equals f of x1, and that'll give us our f1 value. And then we can basically check set the tolerance again. If f1 is less than the tolerance, then we will break. Now if not, then our new x0 is going to be our x1 from before, and then our new f0 is going to be our f1 from before. And then this should be, we need to put this in a loop, so for I in range max iter, we need to indent everything, then we'll return x1. Is this correct? It should look a bit like this Newton's method we did up here. Okay. Now what I'm going to do, I'm going to run this, make sure everything's okay. Now we need a function f. And this f function needs to be multidimensional. And in this case, there's an example function over here that I'm going to use. Just to save time with coming up with a multi-dimensional function. The one thing we want to do is we want to make this an array. So we'll do that. Run that to make sure everything works. Okay, so we will be looking for the roots of this function using this Newton's method function here. Now I need to come up with some initial guesses. So x0 is equal to, so we're going to want an array with a couple zeros in it. So we will have 0, 0. That'll be our array of our initial guesses. And then we should be able to, oh, there was something up here. I believe this f1 here, this capital F1, is going to be a multidimensional. So if we try and compare it to the number up here, 1 times 10 to the negative 10, it will throw us an error. And the way we can actually fix this, just before we even get the error, I believe it's jan_p.linear algebra.norm. If we compare the norm, basically the magnitude of our vector to the, this will give us a scalar compared with a scalar. That should be all right, and it shouldn't throw us an error there. So I'm going to call the function here for function equals fun. This comes from up here. This function is labeled as fun. And then x, our initial guess, equals the initial guess. So I'm just going to run everything here. It should, let's see here. It requires real or complex. Real or complex value inputs. If you want to use Boolean or integer. Okay, this right here, these need to be, we need to add the decimal here to show that these are floats and not integers. Okay, and it gives us the root of our function. So this here, these are both roots of this function right here. And these were expected values to get for this, and basically confirming that our Newton's method function for system of equations with k variables, k functions, works, and we were able to use Newton's method to find the root of a vector n-dimensional function. So thank you all for watching, and I will see you in part 2C.